Okay, recording is started. Okay. Yes. Okay. Okay. So today we will delve deeper into the mathematical sum formulations, because though it is always important to know those things from the physical perspective, from the intuitive perspective, but also we have to do some mathematics to know the deeper insights, so that we can connect to the physical phenomena, right? So today's assignments will be based on that, because the lectures were like that, right, Tathagato?
Yes, sir.
Yeah.
Week 3
So
will like that one. Week 2 or week 3, this one?
week 3. This is week 3. So okay. So I will change it. Okay. I will change this thing.
Okay.
Okay. So there is a typo. So that will be our first goal, to solve some problems based on those lectures, and at the end of the sessions, let's see how, like, if some insights or some understanding further from the lectures will be built or not. That is our main goal. Okay, so let's go. Okay. Probably. Okay. Okay. Yeah. So as I have said earlier, this is my link of the website. You can follow me, and this is the YouTube channel where my this lecture, this assignment sessions will be uploaded. Uh, Probably to you can visit the last 2 weeks sessions, right?
Yes, sir.
Yeah. So that is working. So please check me out in this website, and if you like the videos, then please do subscribe. Okay. So the first problem is, for real gas, uh, there is an expression that is del U partial derivative del U del V at constant temperature is
Sir,
dashed.
are you presenting?
Yeah, is it not visible?
Only the first page is visible. The question is not
Okay,
visible.
okay. Let me just reshare. Thanks that you just just stop presenting and share again. Yeah, is it visible now?
Yes, yes.
Yeah.
The question is visible. It is a
Okay.
bit, I mean, zoomed out.
Yeah, probably that is, since I screenshot the questions and took it and
Oh,
pasted it on there. Like, I will read it out loudly. That won't be a problem. So the question is, for the real gas, the del U del V at constant temperature is dashed. So let's just understand the problem first. That would be a good thing. Okay, so what does this del U del V at constant T mean? Means that how internal energy changes with volume with fixed temperature. Now, as you have already remembered, so for let's just always, our first principle is the minimalistic model, which is an ideal gas. So let's just compare with it. That will be a fine thing. So for Ideal gas, the U is function of T and
TV in also sometimes.
is it true that U is a function of V for ideal gas?
Ideal gas, no.
No. Yes. That is what I was.
Pressure and temperature.
So that will be mainly the temperature, not pressure only. Pressure also. No. This is only the depends on the temperature, right?
Ideal gas, yes,
In
yes,
ideal
yes.
gas, only the kinetic energy is
That's
there.
why those thermodynamic coefficients came into picture.
Exactly, exactly. So this will be like 3/2 nkbt, like this kind of thing, depending on this. So n, for the moment, let's keep it 1, because since there is not mentioned, we are always taking into account only 1 mole or 1 for the one. We will keep it n equal to 1. So for now, for your perspective, if you wanted to know how del u del v at T for ideal gas, what should that be? Shouldn't be 0.
Yes, because temperature is constant and it is not a function of volume.
Exactly. So since we can write it like this, so since T is fixed, U constant, so del U will be 0. So because we are taking derivative of a constant thing, so that will be 0. But here we are given another different thing, that is real gas, another ball game. So for real gas, let me check whether recording is going on, because that would be a disaster. Yeah, it's going on. Yeah. Okay. So for the real gas, so to calculate for the real gas, can you guess from the physical perspective that it should be 0 or something else? It shouldn't be 0. That you can say, right? It shouldn't be 0, because there are finite interactions. There are certain amount of interactions between the molecules. We have in the previous assignment sessions, we have talked about those things, that there should be some pressure correction and the volume corrections. So that too is because of their interactions, volume exclusions, all those things. So here we cannot say for real gas that internal energy is just dependent on the temperature. That depends on the pressure, volume, and all those things, right?
Exactly.
So that shouldn't be 0. That either be positive or negative. So to do you have any answer for that? But can you like from your understanding, can you give it some answer that it should be positive or negative? Like some guess, because since we are clearing the doubts, that should be a good way to address the problem. Any guess?
So as the particles are not point particles, so there must be some volume for those particles as well. So changing volume at that particle will also result in change in the internal energy of the real gas system.
Exactly, exactly. So
But to in what
so
direction, that I cannot answer from physical point of view.
okay, okay. So let's just give it another go. Okay. So if volume increases, what should you expect? The internal energy, the volume of the total system increases, the internal energy increases or decreases? Because if we answer that question, that is precisely the answer, right? If you answer
It
that,
should increase.
it should increase. Why?
Because if volume increases, so we can say that the number of particles has increased. So the
No, no.
internal energy of the system.
Particle number is same. Particle number is
Also for a constant particle
yeah,
system.
yeah, yeah, yeah.
So now if volume is increased, so pressure decreases.
Okay. Okay.
So since
Do
pressure
you,
is
you don't have to be like conscious that you are saying some wrong thing. You just guess something with some logics, because I want you guys to develop an logic, uh, just so that you will feel confident about saying those things, right? That is what I want from you guys. So you just said that velocity, volume is increased. So if volume is increased, those particles will have much more space to interact with.
each other, so interaction energy increases. In that way, also you can say.
Okay.
Like likewise, I also wanted to come to that point only,
Hmm.
that if like suppose we are taking a beaker,
Hmm.
and if volume is increased, so the
Hmm.
pressure is decreased. Suppose
Hmm.
there is a piston on the top of the beaker, so pressure is decreased. That means the piston moves up,
Okay.
the space increases, so
Hmm.
the interaction becomes more,
Hmm.
and
Yeah,
the internal
that
energy
is
becomes more.
more. Yeah, so you can think it is in this way also. So when they are confined in smaller volume, so there will be much more, collisions, and that mutual interactions, the attractive interactions will be much more, because this is long range. So as their distance become less, so there will be the attractive potentials will be less. Just let me draw the potential profile. So the potential profile was like this, right?
Yes, it's repulsive interaction followed by attraction.
So like this. So as this r increases, this this attractive interaction decreases, right? This is decreases. So it so happens that since if there is attractive potential, the internal energy will decrease, right? If there are more attractive potential, the internal energy will be decreased, because this is kind of a negative kind of thing, right?
Yes.
Yes. So that is the cause. But so since they have much more volume, they will behave more like a ideal gas. So there will be no like kind of a attraction interactions between them. So their energy, their internal energy will be increased. So from this point of view, it is clear. But to come to a conclusion, let's do the mathematics. So now this del u del v at constant t, it is actually written as t
First
dt.
thermodynamic equation of state.
Yeah, because this formula will be later you can get from Maxwell equations. Okay,
Yes,
so there
second
will
also.
uh, so from now just remember it, because I think in the lecture also sir has told you to do that, because sometimes it is better to follow that thing, and later we will realize what is the source of
Yes,
these
yes, sir
things.
also told to make sure you know the formula, and then we will derive and see the physical significance later on.
Exactly, because in our school days also we actually know these gas equation, all those things, but later we have, right now when we are studying in great depth, then we are seeing these things. So there will be always some approach, so how, like, what is the what is the center of importance that we want to study. So for now we just know this thing, this formula. So what is the ideal gas equation? This is P RT by V minus B minus minus
A by n
A by
n
A by
square, n square, b square,
B square.
v
Okay.
bar square.
So now if you take this derivative dp dt at constant B, this is sub constant. So this will be only, sorry, Maybe silent. Okay. So this dpdt, what should be the value? This should be
R by
r
V bar minus B.
r by v bar minus b. This is constant. This is not
0.
varying, so this is 0. Now if you put it in this thing, then this guy will be rt v minus b b minus p, and this minus p again put this thing, put this gas equation. So what
Yes,
will you get?
yes.
rt
That RT by V bar minus B will cancel out, and A by V bar square, or A by
exactly.
N square.
Hmm.
N square by B square. Okay.
Yeah. So this will be positive a by b bar square. So this is the our thing. Now a is positive, you know, right, from the previous thing, and v cannot be negative. Volume
V
volume cannot
square.
be. So
Yes,
these
yes.
two things are positive thing. So we can say safely this for okay, sorry,
Oh, it got zoomed in.
zoomed in. Okay, now it is in the scale.
Yes, yes, it is back to original thing.
Okay, so let me write in different region. So since a greater than 0, v bar greater than 0, so del u del v at constant t is always greater than 0 real gas. So this will be this guy. Okay, so now you have this mathematical calculations and the physical understanding, and it is clear, right?
Yes, sir.
Okay, now take some time, like 1 or 2 minutes to get the thing assimilated, and we will quickly jump back to the next question. Okay, can we go to the next thing?
Yes, sir.
Yeah. Okay, so here the question is, what will be the change in the enthalpy when an ideal gas expands isothermally? Okay, this is a good question, because this whenever, so from my younger days, I always from my experience I can say, whenever the statement is very simple, there lies the most difficult concepts or most intriguing concept. So so here this thing, what will be the change in enthalpy when an ideal gas expand isothermally? So what is let's ask thing, what is isothermal?
Constant temperature process.
Okay, constant temperature. Now going at first, let's understand what is enthalpy. Now enthalpy is denoted as H, which is U plus PV. Now this U is the internal energy, P is the pressure, V is the volume. Now changes enthalpy means this is del H, that is H final minus H. Okay. Now you can promptly, for this there is no need of any kind of complex complex calculations. So what will be H initial, U initial plus P initial, V initial? What will be the final? U final, P final, V final. What will be the difference? U final minus UI initial plus P final, V final minus PI, VI. Now let me now just answer me. For an isothermal process, for an ideal gas,
This term becomes 0.
first term is become 0 because
Second term also.
this is 0. Yes, precisely. U is a function of T only. Since isothermal, this is 0. And why it is 0?
Since the gas is ideal.
Since the gas is ideal. Excellent. So this will be a PV equal to nRT. So both thing is this. So PVI is equal to PF VF because T is fixed, right? T is fixed. So always, also we in our school days for the isothermal system we used to do this thing. So we just said that we are given that the temperature is fixed, the volume gets from this to this, what is the pressure. So we used to do this kind of thing. Pi Vi is equal to Pf Vf, the same thing. So from this thing we can say del H is equal to 0. Okay.
Okay, sir.
Okay. So this is easy because now you have actually seen this thing in some process also. Let's say in isothermal means temperature is fixed, one process is there, and you just do this gas from one jar to another jar. So can you say what is this process? This is some kind of process. We have read about this thing.
Isenthalpic process.
Yes, this is isenthalpic process because the enthalpy is fixed. So
Yes.
for an ideal gas, this is isenthalpic. For an ideal gas, for Joule-Thomson expansion, but Joule-Thomson this thing, enthalpy is 0 or changes.
It is 0.
It is 0. So it is actually eventually the Joule-Thomson kind of thing, right? Joule-Thomson effect for an ideal gas.
Yes, in a mathematical format.
Exactly. Okay. So take some time for this. 1 minute, and we'll go to the next problem. Okay, let's go to the other problem. Now, this thing is quite interesting. The question says, which of the following is an exact differential? So, this is quite mathematical, but uh, it is important because, can you answer me, if a function is an exact differential, it is path dependent?
No, it is a state function.
Exactly. So that's why it is very important to know the a function, because whenever we are given a thermodynamic variable, these are function in the phase space. So when the system is evolving, this function is also evolving with some different variable, because this PVT also varying when the system is evolving in the phase space. So we have to know when they are evolving, they are dependent on the path they follow or not. So to measure that, or for that thing exact, to know whether the differential is exact or not, is a good measure of that variable being path dependent or path function or state function. And you know this concept here very well. If you know this concept here very well, it will be useful for different other areas also. When you are doing some kind of complex analysis, probably in mathematics, you have heard about it probably, if you have some general course on mathematics. So there
Yes,
also,
yes, had in first year.
yeah. So same thing here. So whenever we study something, we have to actually relate to the other concepts that we actually built in our different things. This thing actually come from the complex analysis or complex calculus, this kind of things. Because if you know the complex calculus, it is actually a two variable calculus, because there is two variable x and y, one is real and one is complex. So that is one thing, right? Two variable, there is x and y in complex thing, if you think like that. Can you hear me?
Yeah, sure. I
So
went to what?
so when it is complex field, there will be two variables x and y. One is real part and imaginary part. So they actually follow this multivariable or two variable calculus. So from this comes from the calculus only. So this actually uh, a good, actually the basic calculus. Now, if you see this, all the exact differential df, they are written in a fashion where m xy dx plus n xy dy. So what are those m and n? So these are in the form of x and y. Let's just calculate one by one, because we have to at first check for each and every one, and then I have to come to a conclusion. So for first thing, what will be m xy? Quickly,
Yes, sir. M x y. M will be dx 3y square.
3y square.
So to be very precise, 3x to the power 0 y square.
Yes, this will be 6x square. Now to check whether they are exact differential or not, we have to do one thing. We have to check like this. So this will be DLM. So let me write here, because this thing will be interesting. Del m del y is equal to del n del x. So if it is follow this relation, then we can say they are exact differential. Okay. So for here, del m del y is 0, right? sorry, 6y, and
6y,
del n
12.
del x is this 12x. So are this equal?
Never,
No,
not.
not. So if they are not, so not exact. Let's check this one. So here this m will be sin y, n is cos x. So del m del y cos y and del
They
n.
would not be.
These will not be
Because the angles are only different, how they can
exact.
be.
Okay, let me add some page to this. Okay, so the for this one, m will be minus sin y, n will be x. So n is sin y and x. So del m del y is minus cos y and del n del x is 1. Okay, and for the fourth one, this is for C, and for D, m is 51 x square plus y 47 y to the power 4. 51 x square y 47 to the power 4 n equal to 17x cube 188 xy cube. 17 x cube 188 xy cube. Okay. Okay. Looks like this one. Let's just calculate for the to be sure about it. So okay, del m del y is 51 x square plus 188 y cube del n del x. So you see these things. This partial derivative means when we are derivating with this variable, the other variable will be constant.
Yes, exactly.
This is the thing. So this will be 51 x square and this will be 188 y cube. So here, okay, let's me write this thing. Del m del y not equal to del n del x. So for this case, del m del y equal to del n del x. So this is an exact differential. Okay. So the last one is the correct option. Okay. So check these things.
Yes, sir, it is all right.
It's all right. Okay.
Yes.
Okay. Okay. So let's go to the next problem. Okay. So the next problem says, for a monoatomic ideal gas in the electronic ground state, the temperature dependence on volume in a reversible adiabatic process is given by T2 by T1 3 by 2 is equal to V1 by V2. Will this dependence change if the gas is changed to diatomic ideal gas which is in ground electronic state, and why? Now, what is your answer and the logic behind it?
I think it will change
It will change. Why?
because I presume the energy means the internal energy of the system
Yes.
of the gas.
Yes.
So as we move from monoatomic to diatomic, its dependence, I mean the degrees of freedom, it becomes distributed not only it is restricted to translation but also rotation and vibration motion comes into picture. So it will change.
Precisely. Precisely. So let's just dive deep into this. So for this, the this ideal gas in electronic ground state and this thing, temperature dependence, all those things are to make it the problem a bit sound for you guys. But we have to actually see this reversible adiabatic process. So for reversible adiabatic process, what was the equation thing for ideal gas? PV to the power gamma was constant, right? And what is this gamma? What is this gamma?
CP by CB.
What does this say? I know that this is Cp by Cv, but what is this say?
I mean the definition or the term
This term. Adiabatic?
coefficient.
Exactly. This is called adiabatic coefficient. Do you know there is a form of this 1 plus 2 by f?
Yes, sir, I know.
Okay. So there is also one thing 1 plus 2 by f, as Tathagata earlier said, since the degrees of freedom for diatomic gases will change, that's why there will be change. So for monoatomic, what is the degrees of freedom? If equal to,
Monotypic only translation things will come, so it will be 3 for translation.
so this will be 3. So what will be the
Yes.
gamma for this? 1 plus 2 by 3, 5 by 3. So whenever say that this is 5 by 3, so how this 5 by 3 comes, you know? Now this is the cause that it depends on the degrees of freedom, and as the degrees of freedom increases, this gamma also decreases. So for a, let's understand, for a diatomic gas, there is a two gas molecule. So what will be their actually total degrees of freedom for a diatomic gas?
Diatomic ideal gas.
Diatomic ideal.
Temperature is lower or higher.
It's in that regime when you can take into account all the ideal thing. Means ideal
Okay,
means
all the
so
it is linear or non-linear.
which one?
No, diatomic should also be linear. It cannot be non-linear, right?
Yes.
So 3n minus 5
Hmm.
for vibration. So that will be 1. And rotation, a translation is always 3,
Okay.
and rotation is always 2.
Hmm.
So 3 plus 2 plus 1, 6.
6. So you said this is 6. So this gamma should be 1 plus 2 by 6, 4 by 3. But as we know that for a diatomic gas, this is 7 by something like this, 1 by 4, 7 by 5, or 1 by 3, 1.33. What is that for diametric gas? What is the adiabatic constant? What is the value of adiabatic constant?
I forgot.
Let me check it. So this is for diametric gas. This is 1.4. This is 1.4. Means 7 by 5. So this gamma is 7 by 5. So the degrees of freedom is 5. So when you
Yes,
are
yes, yes.
saying
Rotational will be 1.
no, the thing is there is a constraint in here. It cannot these molecules cannot, it can move in two other direction freely, but not in this direction. There is kind of spring kind of thing, right? This is a constant because when there is
Yes, yes. So
bond,
there will be -1
yeah,
for that constant. Yes,
yes.
yes, yes.
So there will be 2 plus 2 plus 1, so there will be 5. So that's why there will be 7 by 5. Anyway, from our question, this is not important, but it is also important to know those things. That's why we are diving deeper into this thing. So this that's why this thing will what will be the right options then? This is option 4.
Option first.
Sorry, option first, because the energy of a diatomic gas is distributed in translation and rotation and rotational motions. Okay, this is the right thing. Okay, just read this thing. I will take just a minute.
Okay.
Okay, I'll just read. Does this see these things, and I'm just coming. Okay. Hello.
Yes, sir.
Yeah. Did you understand why this one translation degrees of freedom will be constant, because there will be
Yes, yes, they cannot move towards each other.
exactly. Exactly. Okay. Okay. So the this problem says 1 mole of an ideal monoatomic gas, 1 mole of an ideal monoatomic gas at initial temperature 300 Kelvin expands reversibly and adiabatically from volume 5 decimeter cube, which is liter, to 10 liter. Calculate this work done in this process. Okay. Okay. So how are you gonna approach this thing?
Normally, so as the gas is mentioned to be a monoatomic gas, so we can calculate the CV. So from that CV T2 minus T1 or
Okay. So you are trying to say that since this is so this is CV, since but this is why are you trying to this CV, because volume is not constant, right?
yeah. So CP,
So no, because this is adiabatic. One information you have, this is adiabatic.
yeah. So
So
from first law
first law du
is equal to dW.
dq plus dw, so this is 0, so you can write safely du is equal
Yes, yes,
to
we can calculate the DU from that monoatomic part.
exactly the way. Then what will be du?
DU is NCV
ncv dt. And
and CV we can calculate from
why this is only
the
cv? Why this is cv? Because cv, I'm not understanding this thing. Cv means like it's dq dt at constant
constant
volume,
volume.
but here volume is changing, right?
Hmm.
Let's just clear this thing. Cv is this, cv is dq dt at constant p. So here actually what we can do, we we know for adiabatic this thing, what is the relation between pv gamma, that is constant, right? Right, this is constant.
Yes.
Okay. Now to do this, let me go to the this thing. So you haven't asked me why this expression comes for monoatomic gas and diatomic gas. We'll understand here this thing. Okay. Because if pv gamma is constant, and since it is ideal gas, so pv will be rt or some kind of means for fixed, this will be something like this. So there will be substitutions like r t by phi gamma is equal to constant, and later we can see that T and V gamma minus 1 is constant. For monoatomic gas, that means T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 2. Understanding my point?
Yes, sir.
Okay. So just see how I'm coming to this point, because this is important. So here T2 by T1 is V2 by V1. Sorry, this is 1. 1. This will be, sorry, V1 by V2
V1 by V2 gamma minus 1.
minus 1. And for monoatomic gas, gamma is equal to 5 by 3. So this one will be 5 by 3 minus 1, this is 2 by 3. So V1 by V2 is 2 by 3. And if you multiply by 3 by 2, all the things, then T2 by T1, 3 by
We will
3.
get the final temperature.
Yes. So from here we can get the final temperature, and since this is reversible, we can see that's RT ln2, because this is ln VF by VI, right? Since this is these things, we can use that equation. This
Which
is
one?
clear. So in the previous class, what we had known, there's for an adiabatic process, this has RT ln2. So we know this final temperature. RT ln2 none means VF by VI, right? This thing we have done. This is. Could you remember this thing
Yeah.
or not?
Yes, 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 yes.
So from here we can calculate the temperature, and then we know that what is the ln VF by VI, and we can calculate it. Let's just check at first what is T2 will be. T2 will be 2 by T1 1 by 3. So this is 2 to the power half, because V2 is larger by 2 by 3. This is T2 will be 300 times half. Okay. Also this relation this relation is also proved right here.
Yes.
Yes. Okay. So now just a minute, let me add on one page. Okay. Okay. Now you do these calculations and see what is the value of this. I will also put this in my calculator. Okay, put this value and see.
Okay.
Actually, okay, hello.
The answer is not matching with any of the options.
Actually, there is a side problem. I did a mistake. This can be used for this one, because this is can be used because this is
This
reversible. This is reversible and also like adiabatic. So for here, we have to actually, your method should be correct, because when you are expanding this thing, then du should be this du should be, let's go back to this thing, this du should be cvdt. Actually, why is so? Can you because can you say why is it so? This is not the correct thing.
no, I thought this formula was only valid for isothermal thing.
No, this is not valid for, because this is actually wrong. What is CV? CV is dqdt at V or dudt at V. What is this? CV is dudt as V, right?
Yes, constantly.
Yes. Actually, here I actually messed it up with real gas equation. So this is completely wrong. Let me write it. This thing is completely wrong. So CV will be du dt at constant V, right? Cp is du dt at constant P. So for ideal gas, du is cvdt, because when you are expanding du, let me write it like this. So u is a function of pvt. So if you write is du,
But that point that CV means molar gas, molar specific heat constant, constant volume. So how
hmm,
does that make sense? Because
how
volume
that,
is the constant.
where
That CV term,
hmm,
the volume is not constant throughout the process. So how can we make use of that CV?
that's why na changing in that process. So means that temperature is changing in that process, and your internal energy will be given like this is means like cv. What does cv mean? Cv means the temperature, change in the internal energy with respect to temperature at constant volume. But here constant volume means like uh, thus from the state you are starting,
Okay.
then you
So
are
for the
changing to
final,
the then you are changing to this thing.
oh,
And when you are taking this du del p, where this thing du dt at constant p
no, one
dt,
thing that here the change here volume and temperature both changes.
volume and temperature both changes
So proportionally changes.
proportionally, not proportionally, with some uh,
I mean, with increase in volume, temperature also increases, and
yes, 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 yes.
so we can say that pressure is constant.
No, that is also not true,
Why?
because if you see pressure is constant in that sense, then it will be a isobaric process, not a iso adiabatic
Ideal.
process.
So the question is a bit tricky one.
Tricky one. So here actually the thing is, the change in internal energy is the heat capacity at constant volume, and the change is the temperature energy. That is why it is defined as like this. Okay. And for an ideal gas, if you see, this thing is actually zero, because if you do this that expansion, then this thing is zero. So what we can say for ideal gas, du is always cvdt. Okay. We have to do actually special actually these calculations, then it will be clear, I guess, if you write it like this, del u del v at constant t or something like this, then it will be concrete. But for now on, just see this thing, du, what is changing the internal energy is cvdt, and try to see what is happening. So if it is du is cvdt, and We have to calculate the CV. So Cp by Cv is gamma, and also Cp minus Cv is R. That way you know, right?
Yes, sir.
So Cv plus R by Cv is equal to gamma. So what we can write is 1 by R plus Cv is equal to gamma. So this is 1 minus, this is gamma minus 1 by R by Cv. So Cv is R by gamma minus 1. Now we know that what will be du. This is T1 to T2 Cv dt, and Cv, there will be some mole. What is the mole number? 1 mole. So no need to worry about that. That will be nR by gamma minus 1 Cv, and this is dt. dt means T2 minus T1. Let's check whether this thing is this. So change in volume will be actually captured by this. What will be the change for the volume will be captured from this thing.
Yes, it is somewhat compromising the thing.
Compromises the thing. So if you calculate this thing, then n is 1, or gamma is 5 by 3 for monoatomic. Gamma is 5 by 3. So there will be 2 by 3. So this will be 2 by 3, and T2 minus T1. T1. So T2 is here, 300 into half to the power 2 by 3. So do the simple calculation and let me know what is the answer right now. Do the same calculation, okay?
Okay, so T1 was what T1?
I'm writing the expression, okay?
Okay,
3R by 2 into 300 to the power 2 to the power 2 to the power. That is the option, right? T2.
yes, 300 comes out as common.
So just do this calculation now also.
Minus 1389 point something. I think it was one of the options.
Minus?
1389. So 96 is close to
So
that.
minus is coming, right? So this is options.
C.
C is the right option. That will depends on the how you are taking the R values and what amount of this thing. So what is the option? Your right option? Your value 13.89 point something.
89.034 or something.
Joule. So this will be close to this one. So this is the right answer.
96 one. Yeah, it is close.
Close. So this is. Now check these expressions once, okay? And while I also
No.
try to, and then we can go to the next thing. Actually, if you do remember, the change in heat is CPDT and change in internal energy is CVDT. That was done, right? If you read it correctly, so CPDT is like, that is how it is considered.
Yes, yes, from that partial derivative also, the right hand side, top left, top right.
Yeah, yes. Why it would be? Because since for PdV is the work done, PdV is the work done. So if PdV is the work done, then for the internal energy thing, when you are taking the du dv or dq dv, then that thing it's fixed. So that will be 0 for the internal energy, and that will only remain is Cv, and one part PdV will be there for the heat. That will come as nRT, because there is PV is equal to nRT equations. So PdV will be nr something equations, nRT equations, or nr will be there, and from there actually you can see this is the thing. Okay,
Okay, sir.
that is the thing. Just a minute. Okay, is this clear? Clear, right?
Yes, sir.
Because this simple CBDT and because there are lots of algebra is going on, that's why it's not like, if you cannot keep track of all those things
Yes, I
at
mean,
one
there
go.
are a lot of stuffs.
So you have to be in practice, because otherwise you cannot like smoothly tell those things. You have to be in
I mean, the concepts are almost equal, but the conversion that to which form I need in
that
that
is
one particular question, that is a matter of concern.
that comes with some some experience, also some practice. Yeah, yeah,
Yes,
that is
yes.
true. That is true. Okay, so this question says, except hydrogen and helium, the Joule-Thomson coefficient for real gases at ordinary temperature and low or moderate pressure is this. Except hydrogen and helium, the Joule. This is quite informative question actually. I will say that, because except hydrogen and helium, the Joule-Thomson coefficient of real gases at ordinary temperature. Because how can you, from physical perspective, how can you know if those A and B values in the real gas thing, it is not given to you, right?
Yes, I mean, it can be anything, positive,
Can be,
negative.
yeah. So this is quite tricky. Tricky means not tricky, it's informative. I will give you the information about it. Let's say at first think about like Joule-Thomson coefficient. So what is the Joule-Thomson coefficient? Muj, right? This is Joule-Thomson coefficient.
Yes.
I will try to actually revisit the thing, that will be easier. Otherwise, I will write something, and that will be actually difficult for you guys. So, for in Joule-Thomson effect, the enthalpy is constant, right?
Yes.
Now, what is enthalpy? H is U plus P P. Okay. Now, if there is a case, you can say that H is a function of P and T. P means V because P or V are conjugate, canonical conjugate. This thing's called canonical conjugate. Okay, canonical conjugate. But if you want to know V, if you get the information about P, you will get the information about V. These are called canonical conjugate. And if you expand it, then if you DH take a differential, then what will be this? Del H, it will vary because this will vary like this. This will vary del H del P at constant T dp del H del T constant P dp. Okay, and this del H del T, this is Cp actually. This is Cp. Okay, because when you are taking internal energy, and because this is specific heat at constant pressure, because this is depending on the total thing, right? It is right. This is clear. So when will be Cp? When Cp becomes Cp, when this P dV means when dV is 0, there will be only internal energy part. That's why Cp is coming. Do you understand my point?
Exactly.
So from that perspective, this is coming. This Cv, because is in the enthalpy there is internal energy and this is work done. And when this internal energy is there but no volume change, then total heat or enthalpy will be due to volume, that is called specific heat at constant volume. And when there is pressure, there is constant pressure, because you know when V is constant, dV is 0, then you can see del H del T at constant P, constant V will be Cv. I'm writing wrong. No, I'm writing wrong. This is the same thing. So this is U means when you are taking into account all those PV in this enthalpy, and you can write it to play with these coefficients. So this is Cp, and now for Joule-Thomson effect, this is 0. Okay. Now for our case, okay, I have done some mistake. This will be dt. So our case minus Cp dt, which is constant enthalpy, is equal to del Hp T dp, which in turn gives minus Cp, okay, del Tp del H is equal to del H del P at constant T. Now this thing, this guy, del Tp enthalpy is mu J, right? This is mu
Yes.
J, right? So how temperature is changing with pressure at constant enthalpy, that is what Joule-Thomson effect says. Now at real gas, to calculate that thing, this is quite actually laborious task to do, okay, because we have to play with all the algebra. Now to go to this detail to see how this thing is unfolding, to know, we have to come from this del Hp del T, from this thing. Now del Hp del T, this thing actually you can write from this thing. What is del Hp del T? So that will be del U del P constant T, right? This is, I'm just taking a differential with respect to P of this equation, sorry, of this equation. I can write this, right? Del U P del T.
with constant P, with respect to P
constant,
at constant temperature.
exactly. Then there will be V if you take respect to V, and this will be P del V, okay, del V del T at constant del V del P, I guess, at constant T. Del V del P at constant T. Okay. Now here also this del U del P, that is also quite we have to play with these things. So U also, here there will be, in the previous slide, previous this thing, U I have written is in this fashion. So let's come to this thing. This U is PT, that says that du is equal to del U del V at constant T, or you can P or V. Here I will write V because there is something like this, and dV plus del U del T at constant V dt. Now if you respect derivative with respect to P at constant T, again constant T, then you can get del U del V,
Okay, so we substitute this thing into the previous one.
exactly, del V del P at constant T plus del U del T del V del T del V at constant, sorry, del D del P at constant T. Now this is 0. Why this is 0? Can you tell me?
Yes, temperature is constant. You're differentiating temperature, so it
Yeah,
becomes zero.
exactly. Now let me add on page to this. Okay, so from here we can use, also we can, actually this is called expansion. We can expand sometimes in Maxwell relation. You will learn this thing. Okay, so this is del U del P at constant T. You can expand it, del U del V del T and del V del P, because this is kind of a one kind of a thing. This what does say in when we are differentiating something, like del U del X. So del U del A and del A del X. So del A del A will be cancel out. Del U del A, kind of this thing.
Yeah, it's like a chain rule thing.
Chain rule
Some
thing, exactly. This is kind of chain rule thing. Now if you this is quite messy, I need sometimes for now if you will put this thing into that, and you will see how this thing this thing will pan out. So del U del P is like this, and put it like this. So del H del P at constant T equals to there will be T del U del P at constant T. So we have written this del U del V at constant T expression in the beginning, I guess, here or here. So we will use this expression T dp dt at constant V minus P. So if you T dp dt constant V minus P, if you put it here, here, this expression, this will be T dp dt. So let me write it here so that it will be this thing del U del V at constant C is T dpdt at constant v minus p. Okay, so these are all come from Maxwell relations. You will learn in the next lesson. So now if you go, okay, just one interesting thing. So this T dpdt minus v, and if you put it here, okay, here, so there will be, and if you common this thing dv dpt, so there will be T dpdt minus v, and this p and this minus p will cancel out. Can you follow me? This is quite jumbled up.
One second, please.
Honestly speaking, it is quite difficult for you to understand. Okay, just let me restate my statement. Okay, so this del h del p del t is this. There is no problem with that. Then we want to find this quantity, and this del u del p constant t we have found like this, and this is part is 0. Now this del u del v at constant t is written as like this. So there is del T dp dt constant v minus p into del v del p at constant t. Now in this expression there is also del v del p at constant t. Okay, now up to that, can you follow me?
Yes, yes, yes.
So now there in this bracket there will be T dp dt minus p plus p times del v del p constant t. So that p and that minus p will cancel out,
Cancel
right?
out, exactly. Yes, yes,
Exactly. So if you come this side, so let me write line by line. So there will be T dp dt constant p minus p plus p into del v del p at constant t. Okay. T dp dt at constant v, minus p plus p and del v del t at constant p. That was there. Del v del p at constant t. This one, this term. Del v del p, I guess. Del v del p at constant t plus v. Now this term I have written here. So now these two term I have written in bracket and v is there. So these two term I have written. So let's just cancel it out. Now we can write del p del t t dp dt t dp dt v. Okay, it's quite complicated. It turns out quite complicated. T dp dt constant v del v del p at constant p v. Now this is the thing. Now this is the thing. Now we can calculate, because all the things are quite in pt vp, this kind of thing. So we can calculate this thing from the gas equation. So what is the gas equation? P.
but the gas is real gas.
But we can calculate, right? V minus b.
Yes, but that second term del v del pt, that will be difficult.
No, that will be difficult. So let's del p del t. So del p del t is r by p prime p. Okay. Now del v del p at constant t, that means del p del v, and we will reverse it out. So del p del v will be
Okay. Same thing,
okay,
same thing.
minus v prime b square with some constant and minus a 2a by v cube. There will be all minus. Can you follow me up to this point?
Wait, won't that be the plus? I mean, the second
Okay,
one.
yes. Okay.
Yes.
Now if you put that into this thing, into this expression, so there will be a tussle between these two. In this, let me write it out. T times R by P minus P times, and this will be 1 by some kind of a T by P minus B square minus 2 by P cube plus P. So this is the thing, and this is quite complicated, but for a given gas it will be given what is this A, B and those things. So it says that ordinary temperature and low or moderate pressure, and you can actually do these things from here on, because
Yes.
this is algebra, and this from here we can actually the the result says that this will be actually positive. Okay, this will be positive because this is this thing, but most
How?
important thing is the how is this positive, that depends on the A, B values. And from here if you do the algebra, and here actually this is quite, it will take time and I cannot discuss all the other
Yeah, yeah.
problems. Probably this will be better if I do the whole calculations and I give you to you guys in the next session. That will be better thing, probably.
Oh,
Probably that will be better thing. And I don't think, because the actually the follow will be like this. Sometimes we do not have to know the exact answer, but the follow will be like this, and if you play around the algebras, then you can get these things. But why this is hydrogen helium Joule-Thomson this thing, this is quite important to know. That is thing, I think probably if you do the algebra, and that is I think quite, I think this will be apparent. I have to do this in detail to show you guys the result, but for now I think this is positive. If you show the curve, this curve, I'm talking about from this TP curve from constant enthalpy, this will be positive. Okay, this coefficient, the slope is always positive. Okay, from that perspective I'm saying. Okay.
okay.
Okay, so now the next question says, the next question okay, why am I gone? The next question says, calculate the work involved when 1 mole of monoatomic gas at initial temperature 298 Kelvin expands reversibly adiabatically from a pressure of 10 bar to pressure of 5 bar. This is also the same thing, right?
Yes, just here the pressure varies instead
I
of
had the
volume.
pressure, but you can get the temperature change
Yeah,
from the
same
pressure.
thing.
Same thing.
Yes, yes. Instead of volume, there is pressure.
So the expression will be the same thing, but we have to actually know the temperature.
Yes,
So
final.
final temperature. So for my ideal gas we know PV gamma is equal to constant. So we have to know with V. So PV is equal to nRT. So from there P is equal to nRT by P. We have to put it here. So P nRT by P is constant. These things are all constant. So P1 minus gamma T to the power gamma is constant. So from P1 1 minus gamma, so we can write the expressions, right, that P1 1 minus gamma T1 gamma is equal to P2 1 minus gamma T2 gamma. So P1 by P2 1 minus gamma is T2 by T1 gamma, and T2 is equal to T1 into, can you follow this, P1 by,
Yes.
because today's class is quite mathematical and algebraic, I would say. That is
Yes.
sometimes because it is important also to do some algebra. So here P1 P2 is P2 to a pressure. So this is 2 times 2 in 1 minus gamma. For monoatomic, gamma is 5 by 3.
Which sometimes it becomes also frustrating if the things do not go as planned for
Yeah,
mathematical treatment.
yeah. And also like it is it breaks your flow
Yes,
because and it is quite in a long class it is also quite difficult to, like, you have to prepare all those things, and also like you have to link those things together, because just because if I prepare a note and I will just do the mathematics, that will also not connect you guys to connect both with the mathematics and to the physical perspective. That is the most challenging, and that is actually so we should do, because you can know the detailed calculation, I can provide it in the later class, but main idea should be there, right? 1 minus gamma, that will be 2 by 3 by 3. Now the same formula, use this same formula. Where that formula goes, this same formula, u is equal to r by 2 by 3 t2 minus t1. So okay, so this is delta u, sorry, delta w is a n r by gamma minus 1 to t2 minus t1. Do the calculations for me. T1 is 300, I guess, 298. 298. So mole is, hello.
yes, sir.
Okay. Okay. So do these calculations. Probably that will be. It's quite. Next class you also try this thing, and I will give you the exact solution, because for this problem, I think it is just. I think if you do the calculation, it will come, but probably there should be some elegant method to do this thing that I have to check, because if you do the calculation, then that should be. So this will be r. Hello.
Yes, I'm doing the calculations.
Okay. 3 divided by 2 into 298 into 2 by 3 minus 1. It is probably like the previous one, same thing.
It is not matching with any of the options.
How much is this coming?
2182.425.
Why so? Okay. There
Did
is
you
a
also
mistake. There is a mistake. Can you say what is the mistake?
mistake?
Uh, this will be minus gamma. Minus gamma. because this is
Which one?
something like this one T2 by T1. This will be 1 minus gamma by gamma, 1 minus gamma by gamma. So for
I don't see your cursor.
okay, can you see it?
Where? No, no, no. I can see the screen, but it is somewhat frozen.
Okay. Now you can see.
The screen is visible, but the cursor is not.
No, the laser point is not visible.
No.
Okay,
Where
just
it is? Just write something so that.
no, just let me stop presenting and again present. Now it is, this laser point is visible.
Yes, yes. Now it is visible.
Okay. So here, when you are doing P1 by P2, 1 minus gamma by T2 by T1 gamma, and we have changed it with P1 by P2 by 1 minus gamma by gamma, then this thing 1 minus gamma by gamma, so then it will be 2 by 3 by 5 by 3. Let me check it with the ink.
Mm-hmm. So 3 cancels out.
Okay, so this will be 5 by 3. This
2 by 5.
exactly, this will be 2 by 5.
Okay.
Ah, so this will be 2 by 5 minus 1. So now if you do the calculation, I think probably it will match.
The screen got, I mean, the presentation got
Yeah,
turned
I
off.
just now you can see it.
Okay.
Hmm. Okay, you do the calculation. I'm just coming. Hello.
So the R part is confusing. I mean, in that question, it is mentioned that 0.08314 liter bar per Kelvin mole inverse,
Huh?
and 1 liter bar is equal to 100
100
joules. So
joules. So mole is mole. So 1 mole. Kelvin is in Kelvin. So you just. Uh,
8.1314 is the same thing. I mean,
ha
if
ha
I
ha
multiply
ha
this,
ha. Yeah.
it is just for creating confusion.
Ha, ha.
It's coming out around 1187.
Okay. So minus of something, right?
No, positive.
No. Why should be positive? 2 to the power 2 by 5.
Yes, it is coming 1.31.
Okay. From that perspective.
Yes.
Okay. 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 And this is so the nearest option is this one, right?
898
Okay.
joule.
Okay, then that is
So, should that be, I mean, that much difference? Should it create?
probably, I don't know. Probably we need to
No,
check.
no. These options are one question. I mean, one of the options that I had
Hmm,
week 2 assignment
hmm,
this year.
hmm,
Week 2 assignment. There was one question, basic question. Some volume difference was given, pressure
hmm,
was mentioned,
hmm,
and what it was, and two volume differences were given, two different pressures were mentioned, and find the difference in work done.
hmm,
So delta W.
hmm,
So my answer came out to be 7.5. The nearest option was 7, and there was also one option,
hmm.
none of the above. Since the
So,
pressure was given, it was around 0.5 atm. So I thought that 7.5, since the pressure is in that quantity, that 0.5,
hmm,
so 7.5 and 7 should not be the same.
hmm. Oh, that's why you ticked none of the above.
And the answer was 7. I
Probably
got one wrong.
for this kind of question there shouldn't be none of the above thing. There will be nearest kind of thing, because if that is none of the above, because that actually used to bother me a lot in my these days. But sometimes you know what to do. This thing bothers sometimes. Yeah.
It feels, I feel bad.
Yeah.
I feel
Yeah. Yeah.
bad.
Yes. Yes. Okay. The last question for today is consider isothermal and adiabatic compression of an ideal gas from same initial pressure Pi and volume Vi to the same final pressure Pf. If V iso and V adia are the final volumes in isothermal and adiabatic compressions, let me go back to the this thing. If final volumes in isothermal and adiabatic compression respectively, then which of the following relation is correct? This you should answer. After that many, after that many knowledge, this you should answer. Question is, one is isothermal, one is, let me draw the curve that will be help you.
Yes, yes. Area will be more. From the slope also we can say.
Okay. So which will be more steeper?
Adiabatic one will be more.
More steeper, right? So this is P, this is P. So they all started in initial pressure, something like this. Let's say Pi and Vi, and this is this is Vi iso and
Area.
this
So
one.
pressure remains constant, so we can draw a line perpendicular to x-axis, parallel to x-axis.
So for one, this thing be idea. So what will be more, pressure or sorry, what will be the
No,
answer?
the line should be,
Sorry, line
parallel
should be the
to x-axis.
with this thing. Sorry. This is for constant volume, I guess. This will be for constant pressure. Let's say this will be like this. So this is PF. This is PI. This is this is VI. So this is VID. So which will be more? Then you said me answer.
ISO,
So
but
probably I have done some mistake.
I think the slope of ISO has become more.
Oh, yeah, yeah, yeah. So which will be more steeper, ISO or Aradia?
Adiabatic will be more steeper. It will have more slope.
So it will be a more slope. So this is compression. Oh, this is compression, right?
So it will be
In
ulta.
the
Opposite.
the graph is right, but this is for expansion.
Just change the axis. No, same thing.
Same thing, but it will start from here, from same thing.
So it will start from here. One will go to the
Uh,
x-axis.
because now if you this thing, and if you do this thing, then this will be idea,
Idea.
and this will be ISO. Because that's the reverse of this thing. This is V. This is adiabatic. Because it's the final destination from the reverse kind of thing. And this is isothermal. So this thing will be V idea will be, so this thing will be correct. Okay.
Okay, sir.
Okay. So that's that. So this is due these calculations that I will give you in the next class. And
Okay.
in this thing, I will discuss it at first quickly, because this all the methodology is done. Only the calculation part I will just quickly go through. Okay. And that's that. And I will see the other thing. Let me stop the recording